Okay, so we've gone over some pretty complex vector addition problems, doing all this vector component stuff. Okay, what we're going to do today is going to look like we're taking a step backwards, but we need to understand how this type of question works. Okay, I generally refer to these as boat questions, well, because they're usually about boats, but they can sometimes be about planes flying into winds as well. Okay, basically we're looking at one vector affecting another, but in the case of velocity vectors. All right, if I am in on a big lake in a boat, and I'm rowing across the lake, but there's a wind blowing, is it going to affect where I end up? It will. Okay, if I'm rowing across, and I'm just aimed straight across the lake, all I'm doing is rowing straight across, I'm not going to end up straight across the lake, am I? Not if there's a wind blowing. If there's no wind blowing, will I end up straight across the lake? Yes, I will, because there's nothing to push me either direction. Okay. Similarly, if I'm rowing across this perfectly still lake and the wind is directly behind me, how's that going to affect me? I'll go faster. Yeah. If it's in my face, slow. Yeah, I'll be just paddling and paddling and paddling. So what we're going to look at now is if I was doing the same situation but on a river. If I'm rowing and I'm aimed directly across the river, am I going to end up directly across the river? I'm going to end up downstream. Okay? My vector's straight across, but the river's flowing at the same time. So I might be rowing straight across, but I'm not going straight across. Okay? I'm going to be going at an angle downstream because the current's going to push me. Now, what if there's a dock on the other side of that river? I need to get straight across the river. What do? Right, I have to figure out about how far I'm going to get pushed, and I got to aim slightly upstream, or maybe in the fast river a lot upstream, so that I'm rowing into the current a bit, so the current will push me back to straight across. Okay, we have to correct for that. Pilots have to do this all the time, right? If they want to fly from Calgary to Edmonton, they don't just point the plane at Edmonton. They'll end up in, I don't know, Lloydminster, okay? It would all depend on the wind strength and wind speed. The wind is going to push the plane a little bit. They have to aim slightly into the wind so they're pushed back on course. We don't notice that because in the end it looks like they're just going straight from Calgary to Edmonton, okay? But their heading might not have been that. Okay? Their heading would have been slightly into the wind in order to account for the direction or the amount the wind would push them. All right, so I want you guys to copy down question number 1 because we're going to walk through it. You might want to just title this in your notes like boat questions, okay? Because you're going to encounter a lot of these. Okay, so in this question, that's my river, by the way. Okay, the question's asking me how far downstream will a boat end up if it's rowed at 1.2 meters per second straight across an 80-meter wide river that has a current of 2.1 meters per second. All right, so I know the river is 80 meters across. And I'm rowing at 1.2 meters per second. So the two vector quantities that are going to affect me are me, the rower, which I've already drawn on there, and the river current. How do I draw those vectors? Shape. She didn't want to volunteer, but she was right. Okay. How do I draw all vectors? We draw them all tail to and head. Okay. So here's me rowing, and here's the current. Okay. The current is going directly downstream. I'm going directly across the stream. Well, does my resultant now push or point the direction we said we would end up going. That's why we add all vector quantities, regardless of whether displacement, velocity, force, doesn't matter. That's why we draw them this way. That way we always end up with a resultant that is the sum of those two vectors. Okay? This is exactly what would happen if I was doing this. Okay? So this would be now not my resultant displacement, but my resultant velocity. Now, it ends up that in this question, I don't actually need to calculate my resultant velocity. This question wants to know how far downstream I end up, not how fast I'm going. So, if I'm rowing across the river at 1.2 meters per second, and the river's 80 meters across, what can I figure out with those two numbers? Time. Okay? I can figure out how long it's going to take me to get across the river. Now, the whole time I'm going across the river, I'm also going down the river. Those two times would be equal, agreed? Because once I get to the other side, I stop doing both. I stop crossing and I stop going down the river. Okay? So I'm going to figure out how long it's going to take me to row across. T equals d over v, right? Just a manipulation of v equals d over t. We know the distance is 80 meters, and we know the velocity is 1.2 meters per second. All right, oh, that's bad luck. It's going to take me 66.6 repeating seconds to get across this river. How do I figure out how far downstream I'm going to be? Okay. Just a second ago, you told me that the amount of time it takes to get across is also the amount of time I'm going down the river. Do I know how fast I'm going down the river? Okay, can I find d? Yeah. Okay. Here's my speed or velocity going down the river. Here's how long I'm going down the river for. Okay. D equals v times t, okay? 2.1 times 66.6, okay? Repeating seconds. Right. I'm going to end up 140 meters downstream when this is all said and done. So these two velocities are happening at the same time, not one after the other. Okay? They're happening at the same time, but we still draw them like they're happening one after the other. Okay, so this is a what we call rowing across type question. Question number 2 is what we call a going across type of question. Okay? If I row across, I don't end up straight across. If I want to end up straight across, then as we said before, I need to head into the current, right? Slightly upstream. Well, this is still a boat question, even though it's a plane. Okay? But in this question here, for number 2, okay, the pilot, what heading will a pilot need to use if she wants to fly due north? So in a question like this, they're actually telling me your resultant is this. Your two vectors add up to this. Okay? They're saying I want to end up going due north. So that means my resultant is due north. Okay? That's my result. She wants to end up flying due north. Okay? There's a wind that's blowing 30 meters per second due east. Now this is going to seem weird. I just drew those two vectors or head to head, didn't I? Why is it okay that I did that? Because the blue line is my resultant. It's not one of the two vectors, it's the product of those two vectors, okay? So I've drawn my wind here, 30 meters per second, okay? My plane can fly at 200 meters per second, and I need to aim into the wind so that I end up doing this. Okay, so I did draw the two contributing vectors, the speed of the plane, the green line, and the wind, the red line. I did draw those tail to head. Okay, my resultant was this blue line. Okay, they're going to end up producing what the question says. So it's almost like, here's the answer, work backwards. Okay, so I drew the result first, and then I drew the other vectors that contributed to it. Because if I drew what we had on that first diagram in reverse, it would have looked exactly like what I just did. I drew the resultant, and then I drew the second vector, and then I drew the first vector. Okay? Exactly the opposite. So this question wants to know the heading. That means they're looking for what? Heading is direction. Okay? So it just wants to know the angle. I know my blue line points due north. So if I've got a wind blowing east and I want to go due north, I've got to go somewhat west of north. Okay? This is something you don't even think about, but you do it. Okay? If you're walking down this path on a windy day, okay, you do this without thinking about it. You turn just a little bit. Okay? You end up going straight down the path, but you turn just a little bit so that the wind doesn't push you off the path. Okay? Same thing, it's actually even more evident if you're on a bike. Okay? If you don't correct for the wind while you're riding a bike, you're going to end up off to the side. Okay? It would be even more obvious if you were skating on a lake. Okay? If you just push yourself in a straight line and just hold your course and it's really windy, you go straight, off you go. Okay? You go off to the side. Okay? You have to actually push yourself into the wind a little bit, and that's what we're doing here. So can I find this direction if I know that side and the hypotenuse? Okay, what trig function am I going to use here? I have the hypotenuse, and I have the side opposite the angle. Sine. Okay, so the sine of theta is going to equal the opposite side, 30, over the adjacent side, 200. Okay, so that'll mean theta equals the inverse sine of 30 over 200. Okay, so that plane is going to have to head 8.6 degrees north of west. Okay, ever so slightly into the wind. Okay, so those are the two kinds of boat questions you can end up with: a rowing across or a going across boat question. Anybody still need that? Okay, I want you guys to try just number 3 for right now. Okay, so it's like the first one we did, but it's going to ask you two things. It's going to ask you to calculate the distance downstream, which we did. Okay, but it's also going to ask you for the resultant velocity. That's the other side of that triangle. We never actually calculated that on the one we did, but it's just Pythagoras. All right, so I'm going to give you a few minutes on number 3, and then we'll go through that one. Okay, so let's have a look at this. So here's our river. Okay, You can row at 4 meters per second, which is like you're an Olympic rower. That's really fast. 4 meters per second. Okay, you're rowing across the river. So here's our rowing speed. It points straight across the river at 4.0 meters per second. Okay, the current flows east at 1.6 meters per second. All right, so there's the two vectors that I have. They're going to produce my overall motion. Okay, since I'm rowing due north, which I already drew. Okay, what is your resultant velocity? All right, so my resultant velocity would be this green line. Okay, so this would be v. It's velocity, so it's a vector quantity, so I would have to find theta. Right? How do I do that if those vectors are perpendicular? What's my next step if I want to find v? Yeah, use the Greek geek. Okay, use Pythagorean theorem here. Right? The magnitude, at least, of my overall velocity is going to be 4 squared plus 1.6 squared. Okay? Doesn't change just because they're velocity vectors. Okay? I still calculate them the same way. I drew them the same way. I calculate them the same way. So 16 plus 1.6 squared. Okay, so we're looking at 4.3 meters per second. Okay, and I need to find my angle. So the way I drew this, I'm going to use tan. I'm going to go tan to the minus 1 of the opposite side, 1.6, over the adjacent side, 4. Okay, 21.8, which is only 2 significant figures, so 22 degrees. And it's touching north and going east, so east of north. Okay, that's my resultant velocity. Now, had I just said that those were meters and meters, you'd been done like that. Okay, but what threw you is it was meters per second suddenly. It had to be different, but it's not. All vectors are added the same way. Okay, part B. It takes me 3.5 minutes to get from here to here. And I want to know how far downstream I'm going to end up. Okay, if I know how long I'm in the river, okay, and I know that the whole time I'm in the river, I'm moving at 1.6 meters per second downstream, how do I find how far downstream I go? I have V and I have T. How do I use those to get how far downstream I end up? Yeah, D equals V times T. Okay, my distance downstream is going to be right there. Okay, that'll be my displacement actually downstream because I'm giving a direction downstream. Okay, I have V and I have T. So 1.6 times 210 seconds. Is that right? And that's 3.5 minutes. All right, so I end up 336. Actually, I still only have 2 sig digs here, so that should be 3.4 times 10 to the 2 meters downstream. Okay, so what I'm trying to illustrate to you here is if I reword or present you a problem in a new way, don't let it fool you. Okay? Was anything that we did in this question mathematically trying? Okay, do Pythagorean theorem, okay, a simple trig calculation, and V equals D over T. Okay? None of those things are going to try your mathematical abilities, not in the slightest. Okay? What's difficult is the context in which I present them. Right? So we have to get kind of used to reading a question and breaking it down to what do I have? What am I being asked to get? Here's my givens. What am I looking for? right? That's what this question breaks down to, okay? Is how well can you interpret the question, okay, so that you can find what it is we're looking for. All right, this one is like the plane question we did. It's looking for the heading. All right, so I want you guys to see if you can get this one. Plane flies at an angle into a wind blowing 75 kilometers per hour due west. The final velocity of the plane is 318 kilometers due north. What direction is it heading in? Okay, let's look at our drawing here first. Right? I have a wind that is blowing 75 kilometers per hour due west. Okay, so there's my wind vector. It says the final velocity of the plane is 318 kilometers due north. So there's obviously a plane's velocity in here that I don't have, but I have the resultant velocity of the plane. So I'm going to draw the plane's resultant velocity right here. Okay, but again, I just drew these head to head. Is that okay? Yes, because this is the resultant. I know that at least one of my vectors needs to end up with its head on the head of this one. Okay? The other vector is the one that produces this. Okay? If the wind's blowing 75 kilometers an hour to the west and I want to end up doing this, the red line, then I've got to do this. Okay? I've got to go slightly east of north if I want to end up going due north with a due west wind. Everybody all right with that? Okay? Those are the tricky ones to draw. Okay? So we have to think backwards. Right? All the question wants to know is, what's the heading? Which way are you going? Doesn't even want to know how fast the plane's going, although we can figure that out too. Okay? It just wants to know what's theta. What direction did the plane point itself in order to end up going 318 kilometers per hour due north? All right, so to find that angle, I have the opposite side, and I have the adjacent side. Okay, so to find theta then, I'm going to use tan, because I have the opposite side, 75, and the adjacent side, 318. Okay, those are the things I have. Okay, so now I'm going to calculate what theta is. Okay, and it should come out to 13 degrees east of north. Are you all right with that one? Okay. So remember, that's a going across question. Okay, the one you did before that was a rowing across question. Okay, try that one. It's more like what we were doing yesterday. Okay? And very much like what you would see on your unit exam. One straight along the compass direction vector and one angled vector. Give that one a try. All right, so we're looking for the displacement of a truck that travels 25 kilometers at 20 degrees north of west. Okay, so my reference direction is west. Okay, and I'm going to go 20 degrees north of that. Okay, so there's the triangle for the first vector. Okay, and then it goes 10 kilometers south. All right, so the tricky part to this is, does that 10 kilometers end up short of this or past this? Okay, well, there's one way for me to find out. How would I find out how big this side is right now before I draw the next line? Right, use sine. And that's what I do sometimes. If I'm not sure, okay, there's no shame in not being sure. Okay, there's lots of times. In this case, I'm not sure. Okay, so I'm just going to go sine of 20 times 25. I'm going to calculate what black y is right now so that I know how long to draw the next vector. Okay? All right, it's 8.5. So good thing I did that because I was predicting it was going to end up short. It actually ends up long, a little bit past it. Okay, so I know now that black y is 8.55 meters south, okay? And now I know that my 10-kilometer south vector should look like this. A little ways past. Okay? There's absolutely no harm in doing it that way. Okay? All right. So, sorry, we just calculated black y. It was the sine of 20 because it was the opposite side times the hypotenuse 25, and it came out to 8.550503. 583 meters south. Okay, and I gotta find black x as well. That'll be the cos of 20 times 25. Sorry, I should show my work. Cos of 20 times 25. Okay, I'll leave you to get a little bit more ahead of me now. Okay, obviously my overall displacement is going to be that blue line. You can draw the triangle this way or this way. It doesn't matter which way you do it. For me, I always like that line outside of my other lines, but it's entirely up to you. Okay, so let's finish this one off here. My next step is that I need to find the green vectors, x and y components, which are ridiculously easy. Okay, it goes due south, so x is 0 and y is 10 kilometers. Okay, and all it does is go straight south, so it doesn't have a triangle to do any calculating with. All right, so that means then that since this vector goes due south, okay, black x and blue x are the same. They're equal. Okay? I only go west in the first vector. I don't go east or west again. Okay? So black x and blue x are the same number. Okay? So I can say that blue x equals black x here, and that it equals 23.492. All right? For my y, I'm going to have to do a little tiny bit of calculating here. Okay? I've got a 10 kilometer south vector and an 8.55 north vector. So green y, sorry, not green y. Green y plus blue y, essentially. I won't draw it that way. Okay. So blue y is going to equal 10 kilometers, okay, negative 10 kilometers, plus 8.55 kilometers. So if we're punching that in here, we're going to have essentially 10 minus our 8.550503. 583. Okay, so we're looking at 1.449 meters for our y. Sorry, kilometers. Okay, and that is south. Okay, everybody all right with that? Now that I have blue x and blue y, can I find out what my overall displacement is? Okay, so same steps as we're always doing, right? Okay, nothing's changed, doesn't matter which question. Okay, I'm going to have the 1.44 squared plus the 23.4 squared. Okay, that'll give me my overall displacement, which will come out to 24 kilometers. Okay, and then I've got to find theta. Okay, theta for me will be tan to the minus 1. The way I drew the triangle of x over y, so that'll be the 23.4 over the 1.44. Okay, and that will give me it'll actually give me a huge angle. That's the one I have on the board there. It'll give me the complementary angle. So second tan of 23.49231552 divided by my answer. 86.5, but I only have two significant digits, so it'll be 86 degrees. And for me, that's going to be west of south. Okay, but obviously you could also get this one, okay, which is the complementary Questions on that one? Hopefully those are getting more and more familiar, and we're getting a little faster and faster at doing them. Okay, so on Monday, we'll probably start our little like map activity thing. Okay, just to kind of break up doing nothing but vector addition problems for days on end. Okay, so we'll probably do that. And then we'll do a bit more stuff to do with vectors, and then we'll be moving on to projectile motion probably by the end of next week. Projectile motion is the last thing in this unit. So your unit exam is going to be in the next 2 weeks, 10 days to 2 weeks. Okay, I'll figure out a date here right away and let you know what that is.